What we're going to do is solve inequalities the graphical way. Inequalities just like this. Now, I know that if I give you this, that you can solve for x, you would solve it just like you would a regular equation, and you would get x is less than something, or x is greater than something, or whatever. For this video, I'm going to assume that we do not know how to do that, and we're going to rely on other methods to figure it out, because there's going to come a time when you see inequalities that look like this that you won't be able to solve algebraically. So it's good to have a couple of different ways of looking at things, so we have multiple ways of figuring out what the answers are. We're going to start with this. Inequalities generally start out that there's something involving x and you want it to be less than or equal to something else involving x. The two functions that we were interested in that I had just shown was we wanted to know where 2x minus 1 was less than or equal to x plus 1. We're going to do it graphically. Now, first I'm going to make a chart. All right. And I'll say, let's say minus 1, 0, 1, 2, 3, 4. So what I'm going to do, what we're looking for here is we want to know which values of x make this expression less than or equal to the values of this expression. So I'm just going to make a table. If I plug in these x values, I plug in minus 1, 2 times minus 1 is minus 1, is minus 2, minus 1 is minus 3. And if I plug in 0, I'm going to get minus 1 out. And I notice that this is a linear equation, so every time I go up 1 in x, I'm going to go up by 2, because that's the slope. So real quickly I can fill the remainder of this out. I could just say 1, and then plus 2 again is 3, plus 2 again is 5, plus 2 again is 7. And similarly with the other one, x plus 1, if I plug in minus 1, I get out 0. And if I plug in 0, I get out 1. And since the slope is 1, I go over 1, I'm going to go up 1 each time. So this will just be a 2, 3, 4, 5, etc. So, looking at the chart, what are the solutions of the inequality? We want to know what are the values of x that make the numbers in this column, or f of x, less than or equal to the numbers in this column. And you look down, and you see that negative 1 is an answer. And let me just remind you, we're looking at less than. So we wanted this. Alright, less than or equal to. So negative 1 is an answer because it makes this smaller than this. So 1 is like I'll just do a little check. What about 0? 0 works also because negative 1 is less than 1, so that works too. What about 1? 1 is less than 2, so 1 is the solution. What about 2? 2 makes them equal, but we're saying less than or equal to, so that works also. And beyond that, it looks like the numbers in the left column are greater than the numbers in the right column, and so this is where the solution set would stop. So if you were just looking at a chart, if you had no other information but what values of x make the left-hand column less than or equal to the right-hand column, you would probably say x is less than or equal to 2 and call it a day. And that's fine, but there's a graphical way to do this also. Now what I'm going to do is I'm going to plot these two functions on a coordinate grid. So I'm going to plot these ordered pairs out, and we'll get another way of looking at the same set of information. So if you want, just kind of make a note of these, because a note of this chart, because I'm going to move it on the side. You might not be able to read it. But the first point will be minus 1, minus 3, and then 0, minus 1, then 1, 1, etc. So let me just plot those out over here. Let me see if you can still see some of it. But the first one, minus 1, minus 3, so that's down here. And then it was 0, minus 1. Now the slope of that first one, it was 2x minus 1. So the slope is 2, so I go over 1, up 2, over 1, up 2, over 1, up 2, and I can keep on doing this. Alright, so this is the graph of, this is 2x minus 1. And then the other one was just x plus 1. I think you can just about see the pairs on there. Right? So minus 1, 0. Right? If I plug in minus 1, I get out 0. 0 goes to 1, so the y-intercept. 1 goes to 2. 1 goes to 2. and the slope of this is 1, so it's just going to go up by 1 each time also. Here's that second one. So here's what that line is. Alright, and that is x plus 1. Now, the question is, from looking at this, can you tell what the answers were? Notice that the original problem wanted, the original problem was asking, the original problem wanted, where is 2x minus 1 less than or equal to x plus 1? So it's asking, where is the green line less than the blue line? Now, when we're talking greater than or less than, if I want to know which of these things is greater and I'm looking at a chart, you're looking at the values of the numbers, right? You're looking at the outputs of this versus the outputs of this and seeing which one is greater than or less. To look at it on a chart, to figure out what is greater than or less than, you have to look at the y values. All right, you're looking at how up they are plotted. So, for example, I know that in the chart, if I plugged in x equals 3, in the left-hand column, I'm going to get out 1, 2, 3, 4, 5, and in the right-hand column, I'm only going to get out 4. So you use this kind of up and down business to compare the relative sizes of these things. The question is asking for what values of x is the green line less than, or the green line underneath the blue line. That's what you're asking when you're asking a less than or equal to. And the answers are values of x. So you just look at the chart and see where, for what values of x, is the green one less. And it's right here. All right, this is where they're equal. So at x is 2, the two expressions are equal, so that counts as an answer. And anything from 2 back will also qualify as an answer for x, because these values of x give me the results that I'm looking for. All right, these results here. In other words, when x is 1, the green line is less than the blue line. You're just looking up and down to compare them with values of compare them like this. Say if x is this number, all right, this number along the x-axis here, the one that's higher up this line is the one that is greater. So for all of these regions in here, right, as I move the thing left and right, the blue line is always on top. So then that's the condition we were looking for, so that's what the answer is going to be. So how we would write this, we would just say the solution to the inequality, this here, would just be x is less than or equal to 2, which is exactly what we got from looking at the chart, right? From comparing the numbers in the chart. When x was equal to 2, they were the same. When x was less than that, it appeared that the numbers in this column were less than these ones, and that's how you got, that's how you figured out the answer. Now, I'm going to show you that you can still do algebra with these things to a certain extent, and it isn't going to change the fundamental answers that you get. So, remember this. I have another sheet here. Okay, so this was the thing that we started with. If we're going to try to solve this algebraically, the first thing that you might want to do would be to, maybe you would want to subtract x from both sides. And that's going to give you a different setup here. So I'll subtract x from both sides, and that'll give me, that'll be x minus 1 is less than or equal to just 1. Now we're going to do this the same exact way and just see what comes out of it. So if I make x minus 1 0, 1, 2, 3 again, what do I get out of here? Let's see. So we really don't need this anymore. From this side, minus 1, subtract 1, I get minus 2. And then the slope of the segment is, the slope of the line is 1, so I just had to add 1 each time, so minus 1, 0, 1, 2, 3, etc. And on this side, they're all 1s, so it's just 1, 1, 1. These are all, because there's no x in it, right? These are all just 1s. There's just a 1 on this side when you subtract it. So try to solve the inequality less than or equal to now. And what do you get? If you use the chart, you get the same information, right? You want this is less than, so 2 is less than, so that's check. Minus 1 is less than 1, so that's check. 0 is less than 1, so that's a check. 1 is less than or equal to 1, so that's a check too. And then it changes past 2. So what I'm going to do is I'm going to do this system graphically again and show you that that when you modify the original equations, when you start doing algebraic operations to them, it doesn't change what the solution is going to be. So to do this one graphically, I'll graph y equals x minus 1 and y equals 1. X minus 1 in green. If I start plotting these ordered pairs, minus 1 goes to minus 2. Alright. Minus 1, minus 2, yeah. 0 goes to minus 1. 1 went to 0. And then 2 went to 1. And we're getting this line here. Alright. And then on the other side, the blue, that was just a 1. So y equals 1 is just a horizontal line there. Alright, so 1. And once again, what are we comparing now? We're comparing x minus 1. We want to know, where is that less than or equal to regular 1. So I re-plot out the system, and we're looking for where the green line is underneath the blue line, and we get, once again, we get x is less than or equal to 2, right? Because here, we move back. For all these values of x, put the green line underneath the blue line. And it's the same solution that we got last time. On top of these, I have what the old two equations looked like. I have them graphed lightly in pencil. But you can see that from taking these two equations and subtracting x from them, we get a new set of equations, but they still have the same solution. Now the point I'm trying to make here is that you can do operations before you go to the graph and start looking for solutions. The important thing is to understand what you are looking for when you are looking at a chart. So if you know how to read a graph, you can do these things pretty easily, no matter how complicated the original expressions are. The one last thing that I want to point out is, before I move on to a different example, is that you could take a good habit to get into when solving these inequalities is to get a 0 on one side. So the original thing, if I just want to do it down here, the original problem was 2x minus 1 is less than or equal to x plus 1. A good habit to get into for solving inequalities, especially inequalities that are more complicated, is to get a 0 on one side. So I'll take both of these terms over here, so I'll subtract x plus 1 from both sides. So if I take away an x, I get an x, and if I take away a 1, I get a minus 2 is less than or equal to 0. This is particularly helpful for us because it's the easiest one to deal with if you're going to look at it graphically. For example, now if I want to plot this, here's the axis. I want to know where is the graph of x minus 2 less than or equal to 0. So if I plot this y equals x minus 2, I know that the y-intercept is negative 2, and the slope is 1. So the graph of this is going to look like this. Alright, just like that. And then what do you have to look at? You have to compare the y values of the line to 0. So it comes down to only needing to look where the graph is either above or below the x-axis. Again, from here it's easy to see that the x values that make this statement true are these ones back here. Alright, 2 is what the cutoff is. So whenever x is less than 2, you know that these values of x make this expression negative. How do I know it's negative? Because it's plotted underneath the x-axis, right? We're looking at the y values of this. We're comparing the y values of this to 0. So it's good to have a 0 on one side because things are easy to compare to 0, right? If you can graph this, you just knock that out right there. And anything less than 0, anything less than 2 is going to be a solution. What's good about this is it can even work on things that are more complicated. Now, I'll do a chart for this one first, but I'll show you how this is probably going to take a little bit of time, and I'll show you how much easier it is to just be able to do a graph without having to go through the chart each time. But it's still good to know how it's done. So, suppose I want to solve this now, and if I go to do it out like a table, I get x. I'll plug in the same old x values. I'll say minus 1, 0, 1, 2, 3, 4, and just see what this comes out to be. So we got x squared minus x, and we want to know where that is strictly greater than x plus 3. X plus 3. So let me do this real quick. If I plug in minus 1, I get minus 1 squared is 1. Minus 1 is 2. Right. If I plug in 0, I get 0. If I plug in 1, I get 0. Right, 1 minus 1. If I plug in 2, I get 4 minus 2 is 2. If I plug in 3, I get 9 minus 6. 9 minus 3 is 6. And we're getting crazy here, but 4 squared is 16, minus 4 is 12. So let me go over to this one. X plus 3, so I take the x value and I add 3. So minus 1 plus 3 is 2. And since it's a line, if I go over 1 unit, I go up by 1 unit, so that'll be 2. So 3, 4, 5, 6, 7. And so, looking at this, we want to know where are the numbers in this column greater than the numbers in this column. If I go back, I might have to go back. Let me just squeeze in a minus 2 here. Forgot to do that. If I put in a minus 2, what am I going to get out? I'll get out of minus 2 squared is 4. Minus 2 is 6. And squeeze in another one here too. And if I plug in minus 2 to this one, I'll get out a positive 1. Write that real small in there. So let's see. Which values of x make this column greater? It appears that 2 is an answer because 6 is greater than 1, so I'll circle that. Negative 1 does not work because it makes them equal. 0 doesn't work because this is less. 1 doesn't work because this is less. 2 doesn't work because this is less. But 6 doesn't work because, I'm sorry, 3 doesn't work because it makes them equal. But what do we have here? We got 12 and 7 here for 4. So it appears like the answers, we only got 2 answers here, so what's going on in between? Well, we could plot these individually on the graph, but I'm going to do it the way that I finished off that last problem, and I'm going to rearrange this and get a 0 on one side. So let me do that, and so let me do that down here. We'll have, because we know that anything that solves this will also solve the transformed version, the x squared. Can you can't see that? X squared minus x is greater than x plus 3. Bring over the I'll bring everything on the one side. X squared minus 2x minus 3 is greater than 0. So we're looking for values of x that make this thing positive. So can I factor this? And it factors into x minus 3, x minus 3x plus 2 greater than 0. And now this is good news. This is what we want, because we know that anything that solves this will also solve this. But this is easier to see. If we go to plot this thing, in fact, I could make a table that just has these things in it, but I'm gonna graph it real quick. All right. We know that it's a parabola, and we know that it's going to open up, and we know that it has 2 zeros. So the zeros are negative 2 and positive 3. So negative 2 is here, positive 3, right, 1, 2, 3 is here. So we know that if we graph y equals x minus 3, x plus 2, right, we know it opens up, it only has these two numbers as 0, so without actually plugging in each individual value and checking it out, I'm just going to say it's going to look something like this. Alright, and that's all that you really need to know, because you can read the answers straight from this if you know what the graph looks like. Since we know that this thing, we wanted to know where is this thing greater than 0. So we're comparing values on the curve, the y values on the curve, with 0. So if the y values are positive, those corresponding x values will be the solutions, and if the y values are negative, the corresponding x values won't be answers. So just looking at the graph, you can tell that the answers are going to be everything greater than this and also everything less than this going back this way. Now, all that you're looking at, as long as you know what you're looking at, the problem is very easy. We're picking these x values here because these x values make the corresponding y's of this, make the values of this greater than 0. So for example, if I plug in x equals, say, 4, what's that going to give me out? That'll be 4 minus 3 is going to be 1 times 6 is 6. So that means 4 corresponds to 1, 2, 3, 4, 5. Actually, it's a point up here. It's a lot more steep. But that's going to happen with every number that's greater than 3, right? If I plug in 5, I'm going to get 2 times 7, which is 14. So that's way up here. And the reason that it's a solution is because it's plotted above the axis. Now, if I plug in these numbers in here, these will not satisfy the inequality. These won't be answers. For instance, if I plug in x equals 2, I know that I'm going to get a negative number out because the graph is plotted below the x-axis. But I'll try it anyway. If I plug in 2, I'll get minus 1 times 4, which is minus 4, which is down here, which means that those numbers that number is not an answer. Or if I plug in 1, I know that I'm going to get a negative number because it's down here, but let me try it anyway. If I plug in 1, I get minus 2 times 3, which is minus 6, so that's way down here. So if you know what you're looking at, if you know how to read these, you can just pick the answers right off of the right from the graph, provided you know how to graph it. But in the beginning, I'm only going to give you ones that are easy to graph, and this can be used to solve more complicated problems like the ones over here. All right, so let's see. No matter how tough it looks, if I give you this, all that you need to know is a little bit about parabolas, and you'll be able to solve it. So I'm looking for values of x that make this inequality true, that make this statement greater than this statement. So I find that it's easiest to do if we get a 0 on one side. So I'm going to bring all these terms over here, and then I'll see what happens with it. So I subtract an x squared, so I get x squared. No, yeah, just regular x squared. Subtract the 4x, so that'll be minus 3x. And subtract the 3, so that'll be minus 4. And we want less than 0. So we're looking for values. Anything that solves this will solve this. So I'm looking for values of x that make this statement true. See if we can factor it. It factors into x minus 4, x plus 1. Yeah, it's less than 0. So we have it all under control now. All we need to do is know generally what the graph looks like. So I'll draw out my axes. Now, again, we know this makes a parabola, and it's 0 at 4. So 1, 2, 3, 4, it's 0. And it's 0 at negative 1. Negative 1 is 0. And we know, since the lead coefficient is positive, that the graph opens up. So if I give a rough sketch of this graph, it's going to look something like this. It doesn't need to be a work of art, because we're only figuring out where is it positive and where is it negative. So if you know that this is the graph of this, and that this number here is 4, and this number here is minus 1, and we're looking for where is the function less than 0, think about it for a second. Tell me the answer. Tell me the values of x that are going to make this less than 0 from looking at the chart. What you get is x is between minus 1 and 4. The solution set is open circle here, everything in between. Because we were looking for where is it below 0. And we know that these values of x make it less than 0 because the graph, the y values, the outputs are plotted below the x-axis. So these x's correspond to negative outputs of this, and that's how to read it right off of that. So the solution set for this would be x is strictly between 4 and minus 1. Just want to do another example here. No matter how complicated it is, this method will always work as long as you know how to plot the graph. So you're looking at this. I want to know where is this greater than or equal to this. Now, for this one, I want to generate up a rough sketch first. So let me just do this, because this one I can do. Suppose I'm just going to tell you that the graph of this one is going to look like this. Now you don't have to understand this right now, but you just have to understand what the result is. This graph looks like this. All right. And this graph looks like this. 2x plus 10, the y-intercept is 10 and the slope is 2. So it's going to be something real big. So we're going to now. So we should be expecting an answer like we want it. So they meet here and someplace out here. So this is where they meet. You see that? Yeah, let's see. So we wanted to know. Wait a minute. Yeah, we wanted to know where is the parabola greater than the line. And from the looks of it, it appears that we're going to get something that's greater than some number out here. Don't know what that is, but we'll figure it out. And less than this number here, all right? Because those are the values of x that make the parabola. It's kind of tough to see up here, but that make the parabola greater than or higher than the line. So let's do it analytically. Let's do it by multiplying it all out. See what we get. Okay, if I square this, you have to FOIL it, so you'll get x squared plus 2x plus 1 is greater than 2x plus 10. And then when we simplify and bring everything over to one side, cancel out these, and you'll have x squared. If we subtract 10 from both sides, you have 1. You get minus 9 is greater than 0. Now at this point, don't be tempted to bring this over. Okay, do not bring the 9 over and then square root both sides. You will get a nonsense answer. All right, do it with the graph. When we split this up, this will factor into x plus 3. X minus 3 is greater than 0. And when we go to graph this up, let's see. We know that again it's a parabola. It's 0 at minus 3, and it's 0 at 3, and it opens up. So it's going to look like this. Alright. And so what's the problem asking for? It wants to know values of x that make the y values of the curve positive or greater than 0. So if this is 3, we figured out this is minus 3. It should be clear from the graph that whenever x is over here, the function is going to be positive. So the answers are out here and out here. Just like we predicted from sketching them up individually, the final answer would either be, if you want to write it looking like an inequality, it would be x is less than minus 3, or x is greater than 3. That's one way to do it. Or if you want to use interval notation, you could say minus infinity to minus 3, open, union with 3 to infinity, open. That's another way to write it. Or just the number line will also suffice. So the bottom line, the last result that I want to get to is if you're given just a graph, all right, and you don't actually know what f of x is and what g of x is, you can still solve inequalities just by knowing what to look for. So these kind of problems are easier because you don't need to do any algebra first. If this is the graph of g of x and this is the graph of f of x, doesn't matter what it looks like. Doesn't matter what the details are. You want to know what values of x make g, or the green line, less than f. All you do is look, and you see where is g underneath. Since this is g, it's underneath through all this region. So they meet here, and here is where they're equal. And so the solutions of this inequality would be x is between minus 1 and 1, 2, 3, 4, minus 1 and 5. These are the answers to this inequality. Now, you don't need to know what the graphs are, but it doesn't matter. You just need to know which one is on top. So that would be minus 1 is less than or equal to x is less than or equal to 1, 2, 3, 4, 5. That's one way to write it. Or the other way to write it would be minus 1 comma 5 bracket. And finally, these things are pretty easy if most of these are easy if you're comparing them to 0. Alright? Because all that you have to do is look for where the function is positive or negative. So suppose this is the graph of some function p of x. Doesn't matter what it is, but if this is the graph, that's all that really matters. We're looking for values of x that make p less than 0. So, which values of x do it? And it's going to be these ones in here, right? Because it's underneath there for these values of x. So that's what? Let me move this up a bit. So right away, that's minus 1 comma 1. Interval notation, it's strictly less than, so I'll leave it open. And if you keep looking over, there's a value over here that also does it, so that's 7. Alright, and it appears that if x is greater than 7, then the curve is also underneath the x-axis. So you would say these answers also count. So that would be minus 1, 1, union with 7 to infinity.